Thank you, Priyanka, and good morning to all the participants. And thank you very much to CII for helping us, sharing this presentation with all of you. In today's, webinar, we'll be talking about the energy efficiency, making manufacturing more productive. What are the various options available in the industrial automation segments which can help us improve in the energy efficiency part. So I'm just starting from the slides and what we'll be covering today is energy demand perspective and drive benefits, various application considerations for energy integration based where we talk about the intelligent motor control concepts, that how the integration helps in improving the performances in the plant, and just a Rockwell automation overview slide that what we are about. This is a very old slide that I have from BE. I would say that not so old, but it was it was released almost in 2000. Energy demand that is increasing um, 32 production of MTOE, which shows that the drastically high. And looking at expectations from the industrial segment, right way, minimize it, and why we are working and have a predictable cost that you can see, and we have to, we do not on the government other aspects to ensure that for the time being. Sure. Okay. I just got of 2 to 3 minutes. We'll network bandwidth some 2 to 3 minutes.
It's a request to all the participants. We are facing some technical difficulties. We will resume in another 2-3 minutes. Please be patient and stay with us. We will resume in 2-3 minutes.
And minimum utilization of resources. When we talk about these things, the key important for any manufacturing industry is the market driver. The market drivers are here the cost volatility. We need to be competitive in the market. We need to manufacture products which are competitive where we can compete in the market. We need to follow the government regulations. There are a couple of compliances like on the environment side, pollution side, or on the safety side that we need to obey. And maybe there are various other based on the manufacturing to manufacturing locations that we need to obey, and we need to use the right automation tools so that the government regulations are met to avoid any penalties. Supply scarcity, we see a lot of supply constraints when it is coal or when it is some other means of resources which are depleting the air. So we need to ensure that there is minimum consumption of input resources with the maximum output possible. And sustainability, there are a couple of corporate initiatives and brand protections that help us act as a key market driver for us to position ourselves in the market so that our products could be purchased. So when we talk about the market drivers, the key important business drivers for any manufacturing that comes into picture are listed out. There are a couple of them, but if you see the majorly, the big one which has a huge high percentage of about 48% is the reduce the total cost of operation. So reduce the total cost of operation is the most important prime goal of any manufacturing location when it comes to the business drivers. And when we talk about the business drivers, there are top energy management challenges. The top energy management challenges have been listed out. There are a couple of them. This is actually an LNS research on energy management which was done in a couple of years before. If you can see that out of the list, the key percentages have gone to energy metrics are not effectively measured in the plant, which is about 39%, and disparate systems and data sources are there, lack of visibility into performances is there, and difficulty integrating with the grid. So there are a couple of things which talk about that we are not actually measuring rightly, in a meaningful way the actual consumptions or energy matrix that is occurring in the plant, and we are also not we have also lack of visibility into the performance, that how a particular equipment is operating. I just give an example. Say for example a fan which was working in a dual with a dual starter, and we were maintaining some X flow from it. We thought that by removing the dampers we could put a variable frequency drive and we can save energy. So we put a variable frequency drive and we maintained removed the damper and we got some energy savings. But we do not actually check whether the uptime of the equipment, uptime of this fan, and whether the process parameter at which it was earlier helping us, whether those are also maintained same at the cost of this energy saving, or we are actually getting an energy saving at some different parameters. So a complete comparison is done when an energy management kind of option is chosen in a plant. So what can be done in order to meet these top objectives? An automation player helps in a wide variety of roles, like they can help with the drives, they can help with an automation tools to support in this way. So when we talk about the energy savings, what we normally do, so what we normally do, if you see that the ratio of spending on motors over its lifetime in a plant, you can see that we buy a compressor or we buy a fan or a pump, we make some X amount of investments, we spend X amount on its maintenance, but we pay a huge amount of electricity bills in terms of its power consumption, which is typically greater than 70% spending on the energy bills, which is a huge cost incurred over the lifetime of this equipment for the operation. And we need to know that whether it is worth that this whole red portion of the energy should be utilized for the operation of this equipment, or we have some alternate means. One such example, that if we are going with a variable frequency drive, for example, in this application for fan, pump or compressors, what we need to do is that we increase the investment cost by some level, we reduce the maintenance cost, and we reduce the red portion of this pie chart, which is the energy consumption, and we get a huge lot of energy savings. So all those applications which have a very high capability to save energies in the plant, like fans, pumps, compressors, they are a key means which can help us in improving the plant efficiencies and improving and reducing the power consumptions. We use variable frequency drives because they help us to save the energy due to the direct speed control. Drives can be used to control the speed of an induction motor directly or any motor directly. Improves process operation by smooth speed control. What does this mean? It means that there are some process parameters. It can be pressure, it can be temperature, it can be flow, etc. that we need to maintain at some values. With the drives, we have a capability to vary the speed of the motor by any small increments, like I can change from 0.1 Hertz to 0.2 Hertz as increment or decrement. So when I have a perfect control on the speed of the machine, I can actually maintain the parameters within the right value, like whether it is speed, it is flow, it is temperature, or it is pressure on the process side. Improves input power factor throughout the speed range and load cycle. If you see that normally the induction motors, they have a very poor power factor, like 0.1 to 0.2 when they are operated under light load conditions. And most of the time when you operate any load, there is a variation in the load on the machine, on the motor, and as the load goes down, the power factor deteriorates, and most of the time we have to pay a high penalty for bad power factor conditions. So with the drives, what we do is that drive maintains a high input power factor because it has an inbuilt capacitor bank into it, so it maintains the high capacitor bank at the input and is irrespective of what is the speed and what is the load pattern on the motor side. It also helps us to reduce the motor stresses and increase the life of mechanical equipments. We know that the drive has soft start and soft stop mechanisms. Like in a building lifts, you might have seen as we go from floor to floor, there is no jerk experienced. So this is because the drive starts and stops the equipment very smoothly and softly through some programming functions. So it avoids any heating, vibrations or transient torques that could lead to the mechanical damages. Normally, an induction motor draws about 600% of start and rush current, which puts a limitation on our starting equipments, the fuses that we use, the transformers or generators that we use at the incoming side. And at the same time, when a big machine is started and it draws about 600% of starting current, the other machines in the same line may experience a voltage dip and they may have some challenges. Now, in order to avoid these conditions, we use a couple of arrangements, like we use sometimes start delta starters, we use soft starters, we use some auto transformer mechanisms, or many a times variable frequency drives also. Variable frequency drives help us to mitigate the start and rush current from 100 to 150% only when we start the motors. And above all, we get all complete motor protections. We do not need to use any specific relays or any specific equipments for the protection of motor or for the protection of output side of the VFD when a variable frequency drive is used on the motor. So these are a couple of key benefits that we actually get in case we use a variable frequency drive on a motor. When drives are being used on the motors and we go to the industrial segments, the applications are broadly divided actually into three parts. One is called a variable torque, second is called a constant torque, and third is actually a constant power. But since constant power applications are very less, they may be when you operate an induction motor above the base speed, like some spindle require applications in automotive industries. They run at a very high RPM, so they are categorized in the constant horsepower range. Otherwise, the most common that we see in any other industry are the variable torque applications and constant torque applications. When we talk about the variable torque applications follow an affinity law. They follow a parabolic curve actually here, which says that the curve between the speed and the power is actually a parabolic in the shape. It's not a straight line. The affinity law here helps tell us that the power is proportional to pressure and flow. Pressure is proportional to square of the speed. Flow is proportional to the speed, and power here with these formulas, we get the power which becomes proportional to the cube of the speed, but at the same time we get torque which is proportional to the square of the speed. It means that if we do a 20% reduction in speed, we get about 40 comparison shown on the energy consumption between a throttling valve and a variable frequency drive on a pump application. The earlier slide, these softwares are typical which are available with the manufacturing vendors, drive vendors. But besides, there are some other softwares which are free, accessible from the websites, which can be used through Android phones, iOS phones also, or from your laptops also. These are the softwares where you can get yourself into these websites, and you can put the required details, and you can actually calculate the ROI and present a case to the management that how much is the saving taking place in these applications. So what are the applications? Those are covered in the variable torque. So there are fans and pumps. Typically, I would say that as a thumb rule, any centrifugal fan, any centrifugal pump, any centrifugal compressor, any centrifugal blower is a variable torque application which has a very high potential of energy saving, like ID fans, FD fans, primary air fans, cooling tower fans, chilled water pumps, cooling tower pumps. These are all variable torque applications categorized, and this is a high potential. And let me tell you also that these fans and pumps and compressors, they are the highest power consumers in any industry. If you go to any heavy industry segments also, like cement, metal, mining, etc., these are the highest components which consume the maximum power in the industries. So it is important that we need to have a very good solution for these high power consumption equipments to reduce the power consumption. And typically in these applications, based on their operation and based on the throttling or based on the process parameters required, we normally get an ROI between 6 months to about 2 years in these applications. So what happens, how do we save in case we have a variable torque application? So when we talk about the affinity laws and all those formulas, so where from they actually generate? If you see that this is the typical torque speed characteristic curves, sorry, this is actually the pressure and the flow characteristic curves of a typical pump shown. We have a pump curve which we actually get from the pump manufacturers as we buy the pump, and based on our plant operations we operate at some operating point. If you see the system curve here denotes that the point at which, the curve at which you would like to operate this pump in the plant. So here typically we are operating at 75 feet pressure overhead, at 1250 gallons per minute is the flow that is required from this particular pump. When we use a throttling system on a pump application to reduce the flow, what we actually do is we are actually throttling the pump at the output. This reduces down the flow, but at the same time it increases the head, it increases the pressure in this case. If you can see the difference between the system curve, open throttle curve and system throttled curve, they are quite different. Well, we know that the physics says that in case you reduce the flow, you reduce the pressure also, because here the process is happening in the reverse conditions, and this excess pressure is getting dissipated on this throttling valve. So in case of a pump application, when we throttle the system, we actually change the system curves and we do not make any changes with the pump curve. Now on the same set of application, if you see that I replace the throttling valve, I keep the throttling valve 100% open and I use a variable frequency drive. Variable frequency drive actually changes the pump curve. So you can see at speed 1 we have one curve, at speed 2 we have other curve. So in this case now, when I reduce the flow, I'm also reducing down the pressure. So I'm actually operating the pump at an optimized condition, which ensures that the required head is maintained and also the required flow is maintained based on the application or based on the process requirements. We have done some case studies where we find that in case we have an ID fan application or any fan application, and we know that in a fan application we can throttle the flow either by using a variable inlet vane, we can use the outlet damper, or we can use a variable frequency drive. If you see that a variable inlet vane is used in this case, and we reduce the flow from 100 to 60%. We get a power reduction from 100 to 62%, which shows there is about 38% energy saving when drives are used on a ID fan with variable inlet vane. When same application was attempted with an outlet damper, you can see in this case that when flow is reduced from 100 to 60%, we get the power reduction from 100 to 86%. It means we have got a 14% saving when we are operating a fan with an outlet damper. So comparatively, this says that inlet vanes are much better efficient as compared to outlet dampers. But when we use a variable frequency drive on these ID fan applications, we have some astonishing results. Like you can see that when you decrease the flow from 100 to 60%, we see the power reduction from 100 to 22% and save about 78% of the energy. This is a huge value which actually contributes, which actually tells us that the ROI of the equipment will be much faster in case we are using variable frequency drives on these energy saving applications. The other set of applications in the industry are constant torque applications, and if you can see here that now the cube on the power formula is missing, is not here. You can see that power is proportional to 2 pi nt and power is proportional to the speed now. Torque is maintained constant. We have a straight line. So it means that if we do a 20% reduction in speed, we reduce power consumption by 20%. So it is neck to neck. So all the applications other than the centrifugal fan, centrifugal blower and centrifugal compressor and centrifugal pump are constant torque in nature. So either drives are required for energy saving on them, or drives will be required for the process requirement for them. Like crane hoists, they need because of the process requirement. Conveyors, they need drives for energy saving purposes and speed controlling also. So wagon tipplers, screw feeders, compressors other than centrifugal compressors, they are all classified as constant torque applications. And as you reduce down the energy, reduce down the speed by 20%, you will reduce the power consumption by about 20%. So it's a neck to neck here now. We have a case study on a compressor application. That compressors, it's a utility which is found almost in every industry, whether it's a small or big manufacturing unit, we find a compressor there. So what we do normally in a compressor application as a conventional control, we will have a receiving tank in a compressor. We will have a pressure switch. The pressure switch turns on and off and engages and disengages the motor with the compressor whenever the pressure requirements are reached. So in this case, on this typical example, we are trying to maintain a pressure of 6.5 kg in the receiving tank. But what happens actually? The pressure builds up and it goes to about 7 kgs till the pressure switch intervenes and disconnects the motor from the compressor or disengages the motor from the compressor. At this 7 kgs of the pressure, this is a high pressure if you see that developed in the line. So probably that our pressure pipelines might have not been designed at this pressure. So there are chances of leakage, there are chances of joint stresses on the pipe due to high pressure. And one big thing, at 7 kgs pressure, the motor gets disconnected from or disengaged from the compressor, and it is operating under no load conditions. So when motor operates under no load conditions, it means that its power factor will be about 0.1. So all these top peaks on this waveform represent a low power factor condition where customers have to pay a penalty in case they do not have any other alternate arrangements on this power system. Then pressure goes down and reaches to a minimum value of 6 kgs. This is called the 7 kgs is called the unloading cycle, and 6 kg is called the loading cycle here. At 6 kgs of the pressure has gone too low now. When the pressure switch realizes that it needs to engage the motor back to the compressor to build up the pressure in the receiving tank. So motor gets engaged back to the compressor. There is a current kick of about 150 to 200% drawn, and pressure starts building up. So in a conventional control, we have a wide surge of pressures from 6 to 7 kgs. We have chances of leakages. We have chances of joint stresses. We have a low power factor conditions. We have a high current being drawn about 1 loop. We give a set pressure command that, say for example, 6.5 kgs is required to be maintained, and a variable frequency drive changes the speed of the compressor of the motor based on the pressure expectations in the receiver tank. So now based on user demand, the pressure in the receiver tank is always maintained at the value of a fixed value like 6.5 kgs here, and when the user goes for a lunch, goes for a tea break, or load is lighter, the VFD runs the motor at slower speed so that 6.5 kg pressure is maintained, and when user demand is full, the VFD runs the motor at full speed so that the required pressure is met in the receiver tank. So with all this said, whenever the speed is reduced by the variable frequency drive based on the lighter load demands, we get an energy saving. One big important point, which is the question which comes in the mind of everyone, that the compressors, they are equipped with oil pumps many a times. So how do we reduce down the speed for oil pumps, because it may impact the cooling? This is true, and that's what we do is that we limit the minimum speed range in the variable frequency drives to about 30 Hertz so that the speed will not go below 30 Hertz, and in case the user demand absolutely goes to a negligible value and still we have to maintain a 6.5 kgs pressure in the receiver tank, speed goes below 30 Hertz, so it will then stop and then go into the unloading cycle. So in that case, so we maintain that feasibility, that possibility in the system, so that the oil pumps are run at the minimum possible speed so that they can maintain the cooling of these compressors. So this is what actually the various advantages we get with the variable frequency drives. There are no loading unloading cycles. And typically I would say that for compressors with cooling pumps, the loading unloading cycle is extended to much higher cycles, less leakages in the pipeline, we have better motor efficiency, we have high power factor all the way under all the conditions, and we have controlled start and stop for the motors. And whenever the demand is lesser, we get energy savings, and we get about ROI for compressors based on the type of compressor and based on the type of load cycle, unload cycles. It is about 1 to 2.5 years as an ROI for these compressor applications. So we know about the basic concept that variable frequency drives help us to reduce the speed, and whenever we have any applications where speed reduction is required, we have energy saving. But it's always not true. If you see that there are a couple of functionalities, features in a drive, and a couple of applications where it can be used, where we do not need to change the speed, but we still can have some savings. Like there's an auto economizer functionality available in the variable frequency drives. We call this idle mode energy saving. Idle mode energy saving means that whenever a load on the motor on the machine is reduced to some certain level, the drive will automatically fold back the voltage to reduce the motor flux by sensing output torque current. So when this is done, this reduces the power consumption without changing the speed. So motor will be running at full 100% speed, but based on the load variations on the motor, which we can actually save some amount of energy, additional amount of energy rather than that we actually get through dual starting. As an example, you can see a conveyor application. The conveyor, sometimes you may need to run it at full speed always, but there is a load variation onto it. Sometimes it is fully loaded, sometimes it is 50% loaded, sometimes it is 75% loaded. So whenever there is a load variation on the conveyor, we will get energy saving on these applications. Another such application is the press. Press is equipped usually with a flywheel, and before the press makes a stamping with the load, the flywheel runs in an idle condition for a pretty longer time. So this flywheel idle run is an opportunity of energy saving. For presses to maintain the SPM, you cannot change the speed of the press. You cannot change the speed of the motor below its maximum frequency. So it is mandatory that in case we want to have some savings, there need to be some different mechanisms what we use as an auto economizer here in such applications. There could be such either myriad examples in the industry where we do not want to change the speed, but at the same time we can save some energy because there is load variation on these equipments, on these machines. The other mode of energy saving could be a soft starter, which is again a fixed starting point. We know that there are a couple of applications where we have a concerns in the starting that big motor. We have sometimes limitations from our power system side, sometimes started from a DG set where limitation comes. Sometimes the equipped motor is bigger, and when it is started, it draws a high inrush current and creates a voltage dip in the line. So because of multiple reasons, we use a soft starter so that the start and rush current can be limited. So when the start and rush current is limited by the soft starter, it helps us to avoid the peak demand conditions, which can otherwise lead to a penalty, because if the peak demand goes high, that comes as a additional charge that we have to pay in terms of energy. So soft starter helps in limiting the start and rush current for some critical applications so that they do not draw a very high current. So soft starters also act as a fixed speed equipments and help in the energy savings by some other means by limiting the start and rush currents. Third fixed operation is that many a times there are multiple pumps, there are multiple motors or multiple machine applications where we need to limit the start and rush currents, and we also need to ensure that the transfer startup of each motor is done in a sequence wise. Like you can see in this particular example, we have 3 motors which are fixed on maybe 3 pumps, 3 compressors, or probably maybe 3 different applications. What we do is we use a variable frequency drive, and we connect the variable frequency drive to the first motor. We start it, take it to the full speed. When the first motor is started, we connect it onto the direct online. So this transfer from drive to dual is bumpless without any jerk experienced by the motor. And using the drive, we are limiting the start and rest current from 100 to 150% for all these applications. Similarly, we can start the second motor, put it on the dual, start the third motor, and put it on the dual. Similarly, we can stop each motor to ensure that there is no stress on the mechanical side, and start and stop is ensured in a smooth way. Okay, smooth start and stop sequence wise each of the motor based on our required. So let me add here that this kind of functionality, a fixed speed bumpless transfer, or what we call synchronous transfer mechanism, is available for big rated motors, typically for medium voltage, where voltage is about 3.3 or 6.6 kV available. Also, there are a couple of applications which demand regeneration, energy saving. System regenerates back whenever slip is negative. Slip, it means that when the rotor shaft is running at a speed which is more than the speed of the synchronous speed, and it happens because the load is actually sometimes driving the rotor shaft. So in that case, it becomes a generator and it starts feeding back. Now the drive that is being used on this machine must have capability that it should accept the power to flow from utility to motor, and in terms of regeneration, it should take the power from motor back to the utility as an energy saving. So this regeneration happens either by overhauling, or it can happen because of the decelerating conditions when you want to stop a machine at a very shorter time. Say sometimes you want to stop a conveyor in 0.1 second. Starting in a 0.1 second means that you need a high braking torque, and for high braking torque, normally these conditions arise when it starts regenerating. In most of the time, we put a dynamic brake resistance, and dynamic brake resistance helps in giving us the braking torque, but that leads to the dissipation of this energy. So now how we decide that we should go for a regenerative active front-end drive, or we should simply put a dynamic brake resistance. Now a cost evaluation can be done with these softwares, which help us to guide that whether putting or investing our money on an active front end or a regenerative system is viable, is good or not. This tells us, this gives us again an ROI, that if I put a drive, active front end drive or regenerative drive on some application like crane, like downhill conveyors, which are regenerative in nature, whether I'll get an ROI, I'll get an benefit or not, or whether it is sufficient to put a dynamic brake resistance and get the process run. Downhill conveyors are we can actually define a return on investment ROI by putting drives on these applications. Other regenerative loads could be like on a paper machine. Sometimes we use a common DC bus configuration where there will be multiple drives connected on a common DC bus configuration to the motors. So one motor may be in the motoring mode, another motor may be regenerating back. So all these energies get accumulated in the DC bus, and when the DC bus overflows or accesses to a certain limit, that energy is fed back to the input utility, as you can see in this configuration. So it helps us energy saving, eliminate the need of dynamic brake resistances also, and also ensure that we comply to IEEE 519 standards, which is meeting harmonics at the input or at the point of common coupling. So when we talk about the various aspects of energy saving, whether we are changing the speed of the motor or we are keeping the speed of the motor fixed, but if you go back to the couple of initial slides that I showed as business drivers, market drivers, we have seen that just an energy saving from an equipment is not sufficient. Just to guess that, okay, I'll put a variable frequency drive on a fan and I'll get about 70 or 80% energy saving. It's not just sufficient for us. What we need to know is, we need to know the actual plant scenarios. We need to know the actual plant conditions in a representable data format, which can help us take a decision that certain equipments are being properly utilized, they are properly being used, and we have actual process parameters meeting with this energy saving. So I may get an energy saving from an equipment but whether that equipment is meeting my process parameters also that I want, and whether the uptime of that equipment is also required, or the equipment was shut down for a couple of days and I'm taking a weekly data and I find that this is giving me a high energy savings. That's not true. So it was not working even for 3 days or 4 days in the week. So that's the important thing that we need. So for these kind of informations, we go to the integrated controller information datas, what we call here as an energy matrix. We see that there has been a lot of communication evolutions. If you see that initially the drives were connected, or the various starters, like it can be a dual starter, it can be a swap starter, it can be a variable frequency drives. They were connected to an upstream systems through multiple discrete wirings to a controller, to a shop floor level PLC. Then from shop floor level PLC, there will be one more network going to the upstream, which is our DCS or centralized control system. This involved a lot of I/O wiring, high cost, and high complexity into it. And if you have to share just one parameter from the drive, soft starter, or dual starter with the PLC, you need minimum one wire. So if you increase the number of wires, the risk of losing that data also increases. There was an evolution further when the discrete bundle wires were replaced with a network. So in this case, you can see that we have two layers of digital communications. From the shop floor side, we have one network, and from the top floor side, we have another network being controlled. Now it helped us improve the process, but there were a lot of limitations, like all the informations were not accessible from the shop floor because there were two different networks. You have to go to the shop floor level PLC to take any particular information. And the difficulty was that in configuring, you need to have multiple expertises on both the networks at shop floor level and at the top floor level, and you need to have an expert who can configure both these systems. So what latest trend has come, there is a single network in the plant, and right, all the equipments from shop floor up to the top floor are integrated to it. So like it's a drive, it's a variable frequency drive, it's an intelligent MCC, it's a dual starter. All these equipments are connected through Ethernet protocol to the upstream side, CCS, or the visualization engineering station here. All the information, like a fan, which can be about 2-3 kilometers away from the centralized control system, I can access all the information with respect to that fan motor at the CCS at the control side by using this single Ethernet protocol. I need to learn about just one protocol, maintain just one protocol, and I can configure in this same protocol, and I can have access to all the information from anywhere in the field because I am connected through single network protocol in the system. So this is what is coming up as one of a very important factor in plants, which will be soon replacing the other networks and duplication or multiple networks or discrete wiring mechanisms in the plants. So it helps reduce cost, faster installation, and real-time data availability at the upstream side. So we at Rockwell Automation call this concept as intelligent motor control. Intelligent motor control concept, it is basically a reference architecture for the integration of motor control devices at the shop floor level. Like you can see here, you have medium voltage drive, low voltage drives, intelligent motor controls, you have soft starters, or you can have a dual starters, which are integrated through an Ethernet IP network protocol to the plant-wide system, control system, which can be a control, visualization, or information system available at the top floor. We help getting a simultaneous real-time control, configuration, and data acquisitions through this integrated architecture. So when we talk about the intelligent motor control concept, the question comes that why I should be implementing in my plant? What are the various benefits besides seeing that we get an integration, we get all the data informations at the centralized level, but what are the other values that I should be investing for this intelligent motor control concept? Why I should move from the discrete wiring system, multiple bundle wiring system, to a single network protocol in the plant? The various values, those are attributed here, are faster time to market, lower total cost of ownership, improved asset utilization, and enterprise risk management. So I'll just share these key values one by one. Whenever we talk about faster time to market, we say reduced development time, reduced commissioning time, and reduced maintenance time. So this is what is coming up as an intelligent motor control concept. Why I should be implementing in my plant? What are the various benefits besides seeing that we get an integration, we get all the data informations at the centralized level, but what are the other values that I should be investing for this intelligent motor control concept? Why I should move from the discrete wiring system, multiple bundle wiring system, to a single network protocol in the plant? The various values, those are attributed here, are faster time to market, lower total cost of ownership, improved asset utilization, and enterprise risk management. So I'll just share these key values one by one. Whenever we talk about faster time to market, reduced commissioning time, and reduced maintenance time, development time, there are some software configurations available, and all the equipments on the shop floor, when they are connected, integrated on one Ethernet protocol, we use add-on profile. This is called AOP. These AOPs for all the equipments are available. So we just take that, click on that particular product, we get the tags automatically generated in the controller. So these tags generated are descriptive in nature. Descriptive means that if it's an output current, it will show output current. So I normally ask a question to some of the electrical engineers in the plant that, do you know to write a ladder logic? Do you know how to write a rung? And if I give you a drive, can you communicate it with the PLC? Most of the time I get an answer, no, we do not know about that. So I challenge them that you can use a Rockwell drive on a Rockwell controller and you can configure it, because you do not need to write any programming rung, or you do not need to write any logic instruction here. So what we do is that we have some defined add-on profiles for each and every product. So we click on that particular product, we get the tags automatically generated. These are descriptive tags, and where the data types are automatically defined. So we do not create any error, or we do not need to refer to any manuals for checking the data type, which normally leads to a constraint whenever you are configuring a controller with a drive. And once the tags are generated, then we select the required parameters through a drop-down menu, which we want to share with the controller and between the controller and between the drive. Like it can be output current, speed reference, speed feedback, voltage, anything that we want. So through data links, we go through a drop-down menu, select those parameters, and once it is done, we download this whole configuration simultaneously into the drive and into the controller. So once this is done, the system is ready to run. So it is so easy a process that you do not actually need to write any instructions separately. And when one drive is completely done on one machine, if I have 100 such similar machines, I can do in a very short time, because the other one, they are simply the copycat functionalities. I copy and I define it for the next job that is available there. So tags are automatically updated as I copy and paste it onto the second job. If the time taken for first job is about, say, 30 minutes, the time taken for the next 100 jobs would be about less than 15 minutes for me. So what I do is that with these kind of configurations, the development time is reduced by almost 70% in the commissioning. And it configuring software, all the parameters, the configurations in one platform, and downloading the same in both the drive and in the controller at the same time. We dynamically select the parameters that we want to share between controller and drive through a network I/O. Automatic generation of descriptive tag names occur here, and there are descriptive data. There are data types which are automatically generated. We do not need to define them. All configurations are saved in the controller as a .acd file that I can use in future whenever it is required. And reuse of codes means that if I have a particular instruction that is written, or if I have, say, one conveyor, I have programmed for it, and there are next 10 conveyors, I can use the same copycat functionality to reuse the same codes. The second concept is called the lower total cost of ownership. This is the most important thing that we have been talking about in past couple of slides, the energy saving and the energy management or energy intelligence. So we know that the motors on the plant floor consume about more than 50% of the energy, and variable frequency drives help us to reduce that energy by depending upon the application. Now here, if it's a variable torque, if you reduce the speed by 20%, you get saving by about 50% in these applications. The important thing is that the saving of the power or the energy from these applications is just not sufficient. We need to use some energy management tools to actually see the utilization of these equipments. So what we do is that we use the energy metric softwares and various other tools which can help us to actually define or give us an energy intelligence to see that how is the power consumption taking place with respect to the utilization of the equipment, with respect to the process parameters that we have been maintaining. And through this trend, which we can be generated in a graphical way, in a presentable way to show to the top management, we take a decision that we are actually going in a right way, we are investing the right way or not. So what we do here, that besides a variable frequency drive, a soft starter or a dual starter, which are integrated through Ethernet protocol to the upstream side, we use the energy management tools, softwares in the control side to actually generate those platforms which can help us actually see the utilization of these equipments in the plant side. The other concept is improved asset utilization. The most important thing, reduce unplanned downtimes and reduce time to repair. So what we want is that from process perspective, the important thing for me is that the machine should run continuously. So I want the machine to run continuously. In case there is anything wrong in the equipment, say for example a drive fails, I should be in a position to start the machine much faster. Okay, so I can go maybe later into the analysis of the failure, that why the equipment has failed, what was the reason. I can do a detailed analysis with the vendor. But currently important thing is that whenever there is a failure, I should be able to start my machine in a very shorter span of time. So what we do is that there are embedded diagnostic functionalities available. Data triggers intervention before any unplanned downtime happens there. You can see that in any of the particular applications, we have some defined data available. Like in this graphical representation, you can see that we have defined that if the temperature exceeds through a certain limit, an alarm will be generated, will be populated on the screen, and we can take a necessary action so that the alarm is acknowledged. In case the alarm is ignored, then second step is to stop the system, because it becomes important from the safety perspective of the equipment. Also, there are various vibration signatures which can help us. Say for example, the motor bearing is not well, there is something wrong in the mechanical side, or there is something some problem from the load side, which can actually take those feedbacks also and compare with the baseline to see that there are some alarms, there are some concerns with the mechanical imbalance side system, and we can take the right condition, so the right action, so that the bad conditions before the trip are avoided completely. You can see similarly, like we can go with an electric motor motor current has gone beyond a certain value, and which was not normal. Like a pump was taking 30 amperes current almost throughout the year, but suddenly we realize that current has gone to 40 amps. So it means that there is something wrong from the motor side, from the load side, why the current has gone high. Now I can define that alarm, and I can actually see the alarm sheet that the current has gone high. I can check the system back to see that why this current has gone high, whether there is any mechanical side issue, any motor side issue, or any load side issue on the system. One big benefit that I was talking about, the immediate startup of the machine, is called the automatic device configuration here. This is basically an arrangement when you put drives on the Ethernet protocol with the systems. So what we get on a midnight, say for example, because why we have specifically mentioned midnight, because during that period we do not have any specified engineers or specialized engineers available in the plant, and in case any breakdown takes place, either they have to be called back from their homes, or we have to see a lot of production loss till the machine is not corrected, maybe till morning time. So here what we do is that in case one of our drive fails at any time, so what we do, we put a new drive. We have an IP address issued by the switch, which is a managed switch being used here. The controller gives it already has a .acd file stored for all these equipments into it, so it gives a configuration, IO configuration into the drive, loads the parameter, and system is ready to start. So what we need is a simple operator can take out the faulty drive, put a new drive, make the power connections, and with the start command, within 40 to 50 seconds, the drive will be ready to run. So we can simply eliminate the shutdown for a longer period in case there is anything wrong with the drive or with the product. Now what next we can do, We can later go with the vendor to analyze that why the particular failure has taken place, for which we can take time. But at least our machine would be starting instantly at that time. So these are the functionalities available, with these kind of configurations that we get. Enterprise risk management, personal safety and equipment protections are most important things that they have become nowadays. And if you see that initially, the European countries, North American countries, they were demanding safety at its best from the vendors, while demand from India was not much. But with the current scenarios and some OEMs supplying to the European countries, North American countries, or also in India also, the requirement and expectations from the safety perspective have increased. Now in India also, the requirements like safe speed torque off or safe torque off kind of requirements are coming up to ensure that the personal safety and equipment protections are maintained. So what we do is that, safety is about reduced exposure to a high potential system which can lead to an injury otherwise. So what we do here in this case, if you see, this is a typical safety mechanism which we call as a safe stop functionality. A cutter blade is working here, and one of an operator wants to get in, so he gives the safe stop command, which can be a cat3. So machine stops completely, goes to 0, and then the doors will open. Then he can go inside, perform the cleaning activities, and as he comes out, he can acknowledge and machine will start again. This ensures that there is 100% safety available in the system, and there is no possibility of personal injury or machine downtime due to some accidents in the plant. So drives can have these kind of, or the controllers or the whole system altogether can have this network safety incorporated into it, so that these mechanisms could be incorporated. Besides this, we have some other safety functionalities that are shared in the prior slide, like arc shield kind of functionality. It is called, it's a very important concept that is building nowadays. Arc shield means that in case any arc occurs, flash flow occurs in the panel, the arc should not be able to come out or create any personal injury. So these panels are type 2B coordinated, which are a high mechanically reinforced designs. And if anybody is working in front or any four corners, four sides of the panel, and arc flashes out in the panel due to any reasons, he will be safe. Nothing will happen to the person. There will be a small vent opening at the top of these panels, and whenever an arc is erupted, that arc will be removed from the top side of that panel. Access to the high voltage bus bars, then he has to switch off the power, only then the shutters will open. Similarly, if you go to the medium voltage drives, the doors are interlocked with upstream VCBs or breakers, and through a safety safety through a castle key arrangement, or probably maybe a some safety solution arrangements. What we do actually in that case, whenever somebody tries to open the door, the breaker at the upstream side will get automatically disengaged. And in case we are using a castle key arrangement, then they cannot at all open the doors unless and until the upstream breaker is not first switched off. So these are all the safety requirements which are available nowadays to meet AN 954 kind of standards, meet category 3, SIL 3 kind of standards, and ensure the personal safety and equipment protections. So I have the last slide which talks about the Rockwell automation at a glance. Rockwell Automation is a global industrial automation company, and good thing about us is that we are only in the industrial automation field. We are not into other fields, like we do not make motors, we do not make transformers, we are not into multiple bundle systems. We are the pure automation company. We have our solution is available from drives, controllers, our plant packs, which is our DCS system, and safety solutions, and some switchgear is available with us. We are about $6.3 billion company global. We have greater than 50% of outside the US presence, while we have maximum presence in our North American US markets also. We have presence in about 22% in the emerging markets, and we serve customers with our two business segments as majorly. One is architecture and software, which covers the plant packs, our DCS system, controllers, micro PLCs, and software portions. And second is the control, power and solutions, which cover the drives, low voltage, medium voltage drives, which cover the various support services incorporated into it. We have a global reach with 20 to 500 employees globally. We have a high rich partner network. We have system integrators and distributors which are close to the customer locations to serve them better and serve them faster. And we are currently present in more than 80 countries globally. So by now Rockwell is more than 112 years old company globally, and we are maintaining the culture of integrity and corporate responsibilities. We have domain experts in our field in the industrial automation, and technology innovation is an ongoing process that is occurring, like based on the expectations from the market, from the customers, from your machine requirements. We have been building, improving our technologies so that we can meet or exceed your expectations. So in the summary, we talked about the energy demand and drive benefits, application considerations for energy saving, like we have variable torque, fan pump, and ID fan case studies. Constant torque, we talk about the compressor as a case study. Fixed speed applications like Economizer, soft starters, and regeneration and energy saving concepts in regeneration. We talked about the integration benefits like intelligent motor control, which covers the faster time to market, faster commissioning, no specialization for starting a drive through a controller, automatic device configuration, and safety aspects. So this is the last slide. Thank you very much for your participation. I would look forward to your questions. So let me go through the chat window and find out that in case there are any questions that we need to answer. So Priyanka, you are in the call.